Let's take a look at Chapter 22, Two Categorical Variables, the chi-squared test. In Chapter 25, we cover two-way tables, the problem of multiple comparisons, expected counts in two-way tables, the chi-squared test statistic, cell counts required for the chi-squared test, using technology, uses of the chi-squared test, independence and homogeneity, the chi-squared distribution, the chi-square test for goodness of fit. Two-way tables. The two sample Z procedure of Chapter 18 allow us to compare the proportions of successes in two groups to either two populations or two treatments of groups in an experiment. When there are more than two outcomes, or when we want to compare more than two groups, we need a new statistical test. The new test addresses a general question: is there a relationship between two categorical variables? Two-way tables of counts can be used to describe relationships between any two categorical variables. Two-way tables, an example. A sample survey asks a random sample of young adults, where do you live now? The table below is a two-way table of all 2,984 people in the sample, both men and women, classified by their age and where they live. Living arrangement is a categorical variable, even though age is quantitative. The two-way table treats age as dividing young adults into 4 categories. Here is a table that summarizes the data. So we have people living in their parents' home, another person's home, your own home, group home, or other. Problem. A. Calculate the conditional distribution in proportions of the living arrangement for each age. B. Make an appropriate graph for comparing the conditional distributions in Part A. Are the distributions of living arrangements under the 4 ages similar or different? Give appropriate evidence from parts A and B to support your answer. That was part C. For 19-year-olds, the distribution of living arrangements was 324 out of 540 for 60%. 337 were living in another person's home out of the 540 for 6.9%. 116 out of the 540 lived in their own place for 21.5%. 58 out of the 540 lived in group quarters for 10.7%. And 5 out of 540 lived in another place for 0.9%. Each age group, age 19, 20, 21, has been given the proportion of people who lived in that type of situation out of the number of people of that age group. So for parents' home, in the 20-year-olds, 378 of the 20-year-olds, of which there were 766, lived at their parents' home for 49.3%. So each calculation, each probability and proportion has been calculated. Now we can make a histogram for each. I called it a histogram because the bars are touching, but it's categorical data, so it's clearly supposed to be bar graphs. But if it was truly a bar graph, there should be space between the bars. Nonetheless, we have a bar graph of the 4 groups, ages 19, 20, 21, and 22. And in each group within the bar graphs, we have each type of living style. Notice that it's parent first, another, own place, group, and other for each one of these, so consistency matters. And on the vertical axis, we have the percent, right? So the percent of the 19-year-olds that live with their parents is 60%, and the percent of 22-year-olds who have their own place is pretty close, right? So that's a nice sign. As you get older, the proportion of people who have their own house increases, or own home, rental or whatnot. The problem of multiple comparisons. To address the general question of whether there is a relationship between 2 categorical variables, we look for significant differences among the conditional distributions of one categorical variable given the values of the other. The null hypothesis is that there's no relationship between the 2 categorical variables. H0 is, there is no difference in the distribution of a categorical variable for several populations or treatments. The alternative hypothesis says that there is a relationship, but it does not specify any particular kind of relationship. Therefore, H0 is that there is the alternative hypothesis is that there is a difference in the distribution of a categorical variable for several population or treatments. We could compare many pairs of proportions, ending up with many tests and many p-values. Bad idea. When we do many individual tests or confidence intervals, the individual p-values and confidence levels don't tell us how confident we can be in all of the inferences. So the problem of multiple comparisons, the problem how to do it, part of it is the problem of how to do many comparisons at once with an overall measure of confidence in all conclusions is common in statistics. This is the problem of multiple comparisons. Statistical methods for dealing with multiple comparisons usually have 2 parts. An overall test to see if there's good evidence of any differences among the parameters that we want to compare, and a detailed follow-up analysis to decide which of the parameters differ and to estimate how large the differences are. The overall test, though more complex than the test we met earlier, is reasonably straightforward. The follow-up analysis can be quite elaborate. Expected count in 2-way tables. Our general null hypothesis, H0, is that there is no relationship between the 2 categorical variables that label the rows and columns of a 2-way table. To test H0, we compare the observed counts in the table with the expected counts. The counts we would expect except for random variation of if H0 were true. If the observed counts are far from the expected counts, that is enough evidence against H0. Expected counts. The expected count in any cell of a two-way table when H0 is true is the row total times the column total divided by the table total. Expected counts in two-way tables. Example. Finding the expected counts is not that difficult, as the following example illustrates. The null hypothesis in the age and living arrangement study is that there is no difference in the distribution of living arrangements, whether it's 19, 20, 21, or 22-year-old. To find the expected counts, we start by assuming that H0 is true. We can see from the two-way table that 1,357 of the 2,984 adults surveyed lived in their parents' homes. The age of the young adult has no effect on their chosen living arrangement. The proportion of those living at their parents' home for each age should be 1,357 divided by 2,984, or 45.5%, 0.455. The overall proportion of young adults living in their parents' homes was 1,357 out of 2,984. So the expected counts of those living at their parents' home for each age are 19-year-olds, which were 540 of them, times that quantity of 0.455. The 20-year-olds is 766 of them, times that quantity, etc. So there is an expected number of 19-year-olds living at home to be 245.57, an expected amount of 20-year-olds to be 348.35, etc. Because if about 45% of people are living at home with their parents, we expect about 45% of 19-year-olds to be there, 45% of 20-year-olds to be there, etc. The overall proportion of young adults living in another person's home was 162 out of the 2,984, which is about 5%, 0.0543. So the expected count of those living in another home for each age are the 540 19-year-olds times this proportion, 0.0543, which is about 29 19-year-olds living at home. The 20-year-olds is 766, the amount of 20-year-olds that there are, times the proportion or probability that you're a person living at home, which is the 162 people divided by the 2,984. So we take the proportion of people living in that situation out of all people living in that situation, and then we multiply it by the number of people in that certain age group, because if about 5% of people are young adults living in another person's home, it's like your aunties or your grandmas, maybe something like that, or even just like a friend's house, possibly, or house, I don't know, whatever. Then you take the proportion, which is 5%, and you expect 5% of 19-year-olds to be in that situation, 5% of 20-year-olds to be in that situation. So 5% of 540 is about 30. 5% of 766 is about 42, for example. The chi-square statistic. To test whether the observed differences among the conditional distributions are statistically significant, we compare the observed and expected counts. The test statistic that makes the comparison is the chi-square statistic. Chi-square statistic. The chi-square statistic is a measure of how far the observed counts in a two-way table are from the expected counts if H0 were true. The formula for the statistic is chi-square equals sigma of the observed counts minus the expected counts quantity squared divided by the expected count. The sum is over all cells in the table. So it's kind of like the residuals from way back. We take the observed count from the cell minus the expected count we thought we should have for the cell. So if it was the 5%, we expect 5% of people to be there. So we take the observed account minus the expected account, square that for each cell, and divide by the expected count. Cell counts required for the chi-square test. The chi-square test, like the Z procedures for comparing two proportions, is an approximate method that becomes more accurate as the counts in the cell of the table get larger. Fortunately, the chi-square approximation is accurate for quite modest counts. Cell counts required for the chi-square test. You can safely use the chi-square test with critical values from the chi-square distribution when no more than 20% of the expected counts are less than 5, and all individual expected counts are 1 or greater. In particular, all 4 expected counts in a 2x2 table should be 5 or greater. Note that the guideline uses expected cell counts. Using technology, we've got chi-square test abilities. The chi-square test is an overall test for detecting relationships between two categorical variables. If the test is significant, it is important to look at the data to learn the nature of the relationship. We have 3 ways to look at the data. Compare selected percents. Which cells occur in quite different percents in the different conditional distributions? 2. Compare observed and expected cell counts. Which cells have more or fewer observations than we would expect if H0 were true? 3. Look at the terms of the chi-square statistic. Which cells contribute the most to the value of chi-square? The test we have been using at this point is generally referred to as the chi-square test for independence. And thus far, all examples have been questioned about whether two classification variables are independent or not. In a different setting, for a two-way table in which we compare separate samples from 2 or more populations, or from 2 or more treatments in a randomized controlled experiment, which population is now one of the variables for the two-way table? For each sample, we classify individuals according to one variable, and we are interested in whether or not the probabilities of being classified in each category of this variable are the same for each population. In this context, our calculation for the chi-square tests are unchanged, but the method of collecting data is different. This use of the chi-square test is referred to as the chi-square test for homogeneity. Since we are interested in whether or not the populations from which the sample are selected are the same with respect to single classification variables. Homogeneous. Sorry. Uses of the chi-square test: independence and homogeneity. I'm butchering the word, I'm sorry guys. Uses of the chi-square test. Use the chi-square test to test the null hypothesis. H0 is there is no relationship between two categorical variables when you have a two-way table from one of these situations. A would be a single SRS with each individual classified according to both of two categorical variables. In this case, the null hypothesis of no relationship says that two categorical variables are independent, and the test is called the chi-square test of independence. Or B, independent SRSs from two or more populations with each individual classified according to one categorical variable. The other variable says which sample the individuals come from. In this case, the null hypothesis of relationship says that populations are homogeneous, and the test is called the chi-square test of homogeneity. The chi-square distributions. Software usually finds p-values for us. The p-value for the chi-square test comes from comparing the value of the chi-square statistic with critical values for a chi-square distribution. The chi-square distributions. The chi-square distributions are a family of distributions that take only positive values and are skewed to the right. A specific chi-square distribution is specified by giving its degrees of freedom. The chi-square test for a two-way table with R rows and R number of rows and C number of columns uses critical values from the chi-square distribution with R minus 1 times C minus 1 for degrees of freedom. The p-value is the area under the density curve of this chi-square distribution to the right of the values of the test statistic. The chi-square test for goodness of fit. The most common and most important use of the chi-square statistic is to test the hypothesis that there is no relationship between the two categorical variables. A variation of this statistic can be used to test a different kind of null hypothesis, that a categorical variable has a specific distribution. The chi-square test for goodness of fit. A categorical variable has k possible outcomes with probabilities p1, p2, p3, ... through pk. That is, pi is the probability of the ith outcome. When we have n independent observations from this categorical variable, to test the null hypothesis that the probabilities have specified values, h0 equals P1 equals P10, P2 equals P20, PK equals PK, K0. So I just 1, 0, 2, 0, K0. Find the expected count for the ith possible outcome as n times P to the ith 0, and use the chi-square statistic. Chi-square equals the sum of the quantity of the observed count minus the expected count squared divided by the expected count. The sum is over all possible outcomes. The p-value is the area to the right of the chi-square under the density curve of the chi-square distribution with k minus 1 degrees of freedom. Example, births are not evenly distributed across the days of the week. Fewer babies are born on Saturdays and Sundays than other days, probably because doctors find weekend births inconvenient. A random sample of 140 births from local records show that this distribution across the days. 13 on Monday, 13 on Sunday, 23 Monday, 24 Tuesday, 20 Wednesday, 27 Thursday, 18 Friday, 15 Saturday. Sure enough, the two smallest counts of births are on Saturday and Sunday. Do these data give significant evidence that local births are not equally likely on all days of the week? The null hypothesis for births says that they are evenly distributed. To state that hypothesis carefully, write the discrete probability distribution for days of birth. So the probability would be P1 for Sunday, P2 for Monday, P3 for Tuesday, P4 for Wednesday, P5 for Thursday, P6 for Friday, P7 for Saturday. The null hypothesis says that probabilities are the same on all days. So H naught is that P1 equals P2 equals P3 equals P4, P5, P6, P7. Everything's the same, which is 1/7. So you have a 1 in 7 chance of having your baby on a Monday or a Tuesday. Equally likely. The alternative hypothesis says that they are not equally likely probable. The alternative hypothesis states that not all PI equal 1/7. Were you trying to get the sand, Eliza? Oh, here. Under the null, all the expected counts are 1/7 of the total count of 140, or 20. So the chi-square statistic is the sum of the observed counts minus the expected count. So each expected count was 20 because there was a 1 in 20, or 1 in 7 probability. So 1/7 of 140 is 20. So each group was expected to have 20 in it. So an expected count of 20. Each group's observed count then takes away the 20 and squares the result. Because we are squaring, we get to add up positive values instead of negatives, possibly canceling out data. So again, we square like we did with the deviations a long time ago at the beginning. The new use of the chi-square requires a new degrees of freedom, one fewer than the number of values in the categorical variable, in this case days of the week, can take. So here df equals 6. Software gives a p-value of 0.269. So these 140 births do not give convincing evidence that births are not equally likely on all days of the week, because a p-value of 0.269 is not a small p-value.